we've learned that Ethereum actually runs on this Keccak 256, but we used SHA 256 for this demo. It doesn't really matter. We're just talking about hashing algorithms. So again, a hash is a unique fixed length string meant to identify any piece of data. A hash algorithm or a hash function is a function or algorithm that computes any type of data into a unique hash. Mining is the process of finding the solution to the blockchain problem. In our example, the problem was to find a hash that starts with 4 zeros. Whenever a node mines a block, they get paid a little bit of that gas we were talking about earlier for doing so. A block in a blockchain is basically a combination of a block, nonce, transaction, and a previous hash to create this unique hash for this block. And again, depending on the blockchain implementation, this might have a couple other fields or might have different fields, but this is essentially what's going on. Blockchains are decentralized and distributed because many independent users are going to run this blockchain software, and it will check and they will compare against each other to see which blockchains are acting honestly and which ones are acting maliciously. In the blockchain world, majority rules. The nonce here is the answer used or the number used to get this hash. Now, nonce is kind of an overloaded term. It's actually used for a number of different reasons. In this case, we're using it to solve this problem of getting 4 or 5 zeros at the stop of the hash. However, in Ethereum, it'll also be often used as the number of transactions from a given address. So now we're going to talk a little bit about signing these transactions and private keys and some other cryptography pieces, right? Because in this blockchain demo here, we can see we have all these fantastic transactions, right? All these things went through, but how do we know that it was Darcy who was the one to send $25 to Bingley, right? How do we know that actually happened? And this is where all those pieces that we just learned about in our testnet, in our MetaMask account, are really going to start to come to life here a little bit here. So here we have an example of public and private keys. Okay, at the top we have this private key, right? That was randomly generated. A private key is as it kind of states, is a key that you really want to keep secret because you're going to be using this as kind of your secret password for all your transactions, right? I can really pick any private key, anything that I want, and with it, this algorithm, they're going to use an algorithm. For Ethereum and Bitcoin, they both use this elliptic curve digital signature algorithm. It's a variant of just a digital signature algorithm, and it's going to create this public key, right? I'm really not going to go at all into kind of this digital signature algorithm, but just know it does use some of the hash knowledge that we just learned, combined with some other pieces to kind of get this public key here. So I'm not going to go too deep into it, but we have this private key that we create, and we get this public key. Now, this public key, we want everybody to have access to, right? This is, whole world can see this. This private key, we really want it to be private. We don't want people to see this. We're going to use this private key as like a password to quote unquote digitally sign transactions. And then people can verify them with this public key. So let's see what this actually looks like. Let's pick a random key, a more secure key, right? Because the longer it is, the more secure it's going to be. And if we go to signatures now, right? Let's say we have this message that we want, right? We'd say hi world, right? We want this to be the message. What's going to happen is this private key that we've created, we can use to sign this data, right? Remember how in the blockchain demo, we were hashing stuff, right? We're using this SHA-256 hash to get this hash. Well, we're doing something similar, but instead of hashing, we're using this digital signature algorithm to create this message signature. Now, what's really powerful about how this algorithm works is that you can create this message signature with your private key, but somebody else can't derive your private key from the message signature. And that's what makes this really, really powerful. However, if we go to verify using this public key, right? And so this is that 0403. This is that same public key. Using this public key, anybody can verify. Oh, let's go ahead and sign it again. Anybody can verify that this signature is yours, right? So you have a private key just for you, so you can sign things, and a public key so that anybody can verify something, right? So anybody can verify this, and let's say somebody tries to fake a transaction from you. They say, "Hey, this is their transaction." All they have to do is verify that this signature against your public key, and very easily, this whole thing turns red because it isn't verified, right? The algorithm says, hey, that's wrong. So we can go ahead and take that into transactions in this exact same way. So if I want to send money, if I want to send $400 from, my address to another address, using my private key, I can sign that transaction. And anybody else in the world can then verify this transaction, right? And this is why when people say, hide your keys, protect your keys, this is what we're talking about. In our accounts here, right? If we go to settings, and again, the only reason that I'm showing you guys my mnemonic and my private key is because this is a dumpster account. I'm going to throw this away at the end of this video, or I'm just not going to put any real money in it. But when we look at our MetaMask here, we have this mnemonic phrase, which allows us to easily get these different private keys, right? So mnemonic phrase combined with, whatever account number will get us a private key. So mnemonic phrase combined with 1, we're going to get this private key. And this is when we look at account details, export private key, password confirm. This is going to be the private key that we're going to use to sign our transactions, right? This, if anybody else gets access to this private key, they then can sign transactions for us, and they can send transactions for us. And that's why we want to keep these private. So it works the exact same way, right? And so this is why it's so important to hide your private keys and hide your mnemonics. Now, your Ethereum address is actually a piece of your public key. Now, to get our address in Ethereum, all we have to do is take this public key that we've created with our private key, hash it using that same Ethereum hashing algorithm, and then take the last 20 bytes. And that's how we'll actually derive to our address here. Now, knowing the exact methodology of how to get the address doesn't really matter because it could change blockchain to blockchain and could even change in ETH2. But just know that that is essentially how kind of these addresses are derived, right? There's some derivative of the public key, right? Because the public key is public, and using the public key in kind of any public way is totally fine, but not the private key. So that is how we sign our transactions. Note though, this isn't how we send the transactions. So this is just going to sign it, create a transaction for us to send. We'll learn later on how to send these transactions. Whew, so that was a lot of information there too. Let's do a quick recap. Your public key is derived by using a digital signature algorithm on your private key, right? And you want to keep your private key private at all times because you're going to use your private key to sign transactions. Signing transactions with your private key, you are the only one who can actually do this because you can't get the private key from a message signature. However, using your public key, anybody can very easily verify that a signature that's signed by you is in fact signed by you. In our MetaMask, our private keys are located in this account details section. You just hit show private keys and type in your password, and you'll get your private key here. A quick note here is oftentimes when using your private key somewhere, they want it in hexadecimal form. So if we're going to use our private key for something like Brownie, which we'll go into later, we need to actually append a 0x to the front, but we'll get into that later. And the address of your account is derived from this. So if you think about it, your private key creates your public key, which then can create your address. And there's a little barrier here, or a big barrier here, because your private key you want to keep private, and your public key and your address can all be public information.
Awesome. So now that we know all the cryptography pieces and all the little nitty-gritties of how the blockchain actually works and how our signatures work and how everything sticks together, let's talk a little bit about how this works in actuality and what's really going on. Now, for a lot of this, each different blockchain has slightly different algorithms and slightly different metrics and criteria for doing a lot of this stuff. So when we're talking about these specific implementations, keep in mind the exact algorithm might be a little bit different, but the concepts are all still going to be exactly the same. Hashing and a hash function is going to be the same no matter where you look. A decentralized blockchain is going to be the same no matter where you look. How it's actually implemented is going to be a little bit different. Now, traditionally, when you run an application, be it a website or something that connects to some server, you are interacting with a centralized entity. And unlike how we saw with the blockchain with multiple different peers, it's going to be run by a single centralized group. Now, it still could be run on many different servers, but all those servers are still going to be controlled by the same centralized group. Blockchains, as we saw, run on a network of different independent nodes. When we saw peer A, peer B, peer C, those were different examples of different independent users running the blockchain technology on their own node. Now, when I use the term node, I'm usually referring to a single instance of a decentralized system. So when I say a single node, when I'm talking about a blockchain, I'm talking about one of those peer A's, peer B's, peer C's running that blockchain software. I'm talking about one server running this technology. And again, it's this network, it's this combination of these nodes interacting with each other that creates this entire blockchain. What makes these so potent too is that anybody can join the network, and that's why there's decentralized. The barrier to entry is a little bit of hardware requirements, you getting the correct materials to run the software, and then you running the software. Anybody can join these networks and participate, and that's what makes it truly decentralized. In fact, you can go to GitHub right now and run your own Ethereum node in a few seconds. Now, in the traditional world, applications are run by centralized entities, and if that entity goes down, or is maliciously bribed, or decides that they want to shut off, they just can't, because they're the ones that control everything. Blockchains, by contrast, don't have this problem. If one node or one entity that runs several nodes goes down, since there are so many other independent nodes running that it doesn't matter. The blockchain and the system will persist so long as there is at least one node always running. And luckily for us, most of the most popular chains like Bitcoin and Ethereum have thousands and thousands of nodes. And as we showed in our demo, if one node acts maliciously, all the other nodes will ignore that node and kick that out or even punish it in some systems, because they can easily check everybody else's node and see, okay, this one is out of sync with the majority. And yes, majority rules when it comes to the blockchain. Each blockchain keeps a full list of every transaction and interaction that's happened on that blockchain. And we saw if a node tries to act maliciously, then all their hashes are going to be way out of whack and they're not going to match everybody else. This gives blockchains this incredibly potent immutability trait where nothing can be changed or corrupted. So in essence, we can think of a blockchain as a decentralized database. And with Ethereum, it has an extra additional feature where it also can do computation in a decentralized manner. Now let's talk consensus, proof of work, and proof of stake, because you've probably heard these before and they're really important to how these blockchains actually work. When we went through that blockchain example and we did that mining feature, this is what's known as proof of work. Proof of work and proof of stake fall under this umbrella of consensus. And consensus is a really important topic when it comes to blockchains. Consensus is defined as the mechanism used to reach an agreement on the state or a single value on the blockchain, especially in a decentralized system. I briefly alluded to this consensus mechanism in our blockchain example when I said if one changes something and the other two don't, then majority will rule and kick that one out. This is part of that consensus mechanism. Now, very roughly, a consensus protocol in a blockchain or decentralized system can be broken down into two pieces: a chain selection algorithm and a Sybil resistance mechanism. That mining piece that we were doing, or the proof of work algorithm, is what's known as a Sybil resistance mechanism. And this is what Ethereum and Bitcoin currently use. Please note that depending on when you're watching this, if ETH2 is out, then it's no longer proof of work. Now, proof of work is known as a Sybil resistance mechanism because it defines a way to figure out who is the block author. Which node is going to be the node who did the work to find that mine and be the author of that block so all the other nodes can verify that it's accurate. Sybil resistance is a blockchain's ability to defend against users creating a large number of pseudo-anonymous identities to gain a disproportionately advantageous influence over said system. And in layman's terms, it's basically a way for a blockchain to defend against somebody making a bunch of fake blockchains so that they can get more and more rewards. Now, there are two types of Sybil resistance mechanisms that we're going to talk about here, namely proof of work and proof of stake. Let's talk about proof of work a little bit more in depth first. In proof of work, this is Sybil resistant because a single node has to go through a very computationally expensive process called mining, which we demonstrated earlier, to figure out the answer to the blockchain's riddle of finding that correct nonce or whatever the blockchain system has in place. In proof of work, this works because no matter how many pseudo-anonymous accounts you make, each one still has to undergo this very computationally expensive activity of finding the answer to the proof of work problem or the proof of work riddle, which again, in our demonstration, it was finding a nonce with that first 4 zeros. But again, each blockchain might change the riddle or change the problem to be a little bit different. In fact, some of these blockchains make this riddle